In another experiment, we took the same 20-meter string and tensioned it at 5 newtons, then at 10 and 20 newtons, and we allowed the string to swing back and forth with an antinode in the middle, that is, with a maximum displacement in the middle, very little displacement at the ends. Even at the end that we were swinging, we were only moving back and forth a couple of centimeters, and out here it was moving 20 or 30 centimeters. So that our end was essentially a node with very little displacement. This end, of course, was tied to a tree. There wasn't much displacement there. So at the 5 Newton tension, we observed that a complete cycle of this string took about 1.8 seconds. That is, we measured about 5.5 cycles in 10 seconds. Now, we didn't trouble to take very, very accurate measurements because this was done more or less as a class demonstration. Then students were asked to repeat it with more precise measurements, as distant students will do. Okay, we're going to observe that this configuration in the string, at any instant the string is either like this, or it's like this, or somewhere in between. But that corresponds to a wavelength, which is a complete cycle that's twice as long as the string, because what we have from here to here is only half of the complete cycle. Now, as we'll discuss and as you've read, we think of a wave moving this way. Well, let's see, if we're at this end of the, well, let's say we're at this end of the string. Okay. If we think of the wave moving this way, there's a reflected wave that comes back on the other side, opposite to the wave that we're sending down. And if the waves have just the right wavelength, they'll match, and when we add the two waves, we'll get this configuration in the string. And the wavelength of the wave that'll match is the 20 meter, is the one whose half wavelength is 20 meters. And that'll give us this mode of vibration. So that if we have this mode in a 20-meter string, that means that we have essentially a wavelength of 40 meters. We're sending a 40-meter wave down, it's meeting itself coming back and causing this reinforcement, this mode of vibration, this resonance here, because this is actually a resonance, also called a fundamental mode of vibration. Okay. Now, if a cycle takes 1.8 seconds, the half cycle that corresponds to the length of the string takes 0.9 seconds. That is, half a cycle of the wave will move the 20 meters of the string in the 0.9 seconds. And it follows then that the wave moves 20 meters in 0.9 seconds, or that the velocity is approximately 22 meters per second. Now we compare that with the 25 meters per second that we got before. It's not a real bad comparison, but we would have liked it maybe to be a little bit more accurate. Repeating for the 2 rubber band and 4 rubber band tensions, we got very commensurate results, a little bit less than what we observed for the pulse going down the string and back. Now, it could be that in waving the string back and forth, we let the tension slack up a little bit. Okay? We were supposed to be watching that, but we might not have been watching it quite closely enough, and that could have something to do with the fact that this didn't come out precisely the same. However, we see that our velocities here run maybe about 10% lower than the velocities we observed for the pulse, whereas the velocities we predicted from the square root of t over mu ran about 10% higher than those we observed for the pulse. It's not clear exactly why the results were a little bit off, but the agreement still isn't bad. We're within plus or minus 10% of our middle values at least.